So hello everyone. Our project is about full stack image super resolution with deep learning. In this project, we have tried to address the problem of converting low resolution images to high resolution ones by using some advanced deep learning techniques. So the reason we chose this topic to work on is that image super resolution has some significant applications in areas like medical imaging, satellite imagery, and even video streaming. So it is a great learning opportunity for us to be able to work with some advanced machine learning tools, which have significant applications in the future. Um, so we have developed over here an end-to-end pipeline by integrating our deep learning models into a user-friendly application. So here users can upload their images and see the results for themselves along with some performance metrics. So to give a little bit background about image super resolution, traditionally methods like bicubic interpolation were used, but these often resulted in blurry outputs and sometimes they used to miss out some fine details. But the field of deep learning has revolutionized this. Um, our project employs three advanced models: SRCNN, VDSR, and EDSR. So more in detail about these models later, but these models basically leverage convolutional neural networks. They extract some complex patterns and significantly improve image quality. And to bring our work to practical use, we've also developed a web application that allows users to upload and generate high resolution images. Now, on to the literature review that we performed for our project. Super resolution using deep learning has made quite remarkable progress in the recent few years. So, one of the foundational methods was super resolution convolutional neural network, which is SRCNN. So, this is a simple three-layer network that has set a benchmark by learning direct mappings between low and high resolution images. So building on this, there's the VDSR or Very Deep Super Resolution Network. This was introduced. Uh, this introduced deeper architectures which had residual learning as well. Then there's the Fast Super Resolution Convolutional Neural Network or FSR-CNN, which improved computational efficiency with post upsampling and enabled some really effective real-time applications. Another big breakthrough came with the efficient subpixel convolutional neural network or the ESPCN. This rearranged pixels across channels for efficient upscaling. And this is especially useful in video tasks. Then there is the generative adversarial neural networks, or GANs like SRGAN. This added an extra feature of adding some realism to the outputs by combining perceptual and adversarial losses. There are some more recent innovations in the field as well, like residual channel attention network and deep blind super resolution. These incorporate the attention mechanism and perform really well. Now, on to the methodology that we have used. Firstly, the dataset that we've used is the div2k dataset. It provides paired low resolution and high resolution images. And the way the data is presented is it has 800 training samples and 100 validation samples. Now, on to the pre-processing part for the data. So the low resolution images in the dataset are divided into different scaling factors like the 2x, 3x, and 4x. So firstly, we load and sort the image pairs. Next, we convert the images to YCBCR color space. And our focus over here in this color space is on the luminance channel, which contains the most critical details for super resolution. For high resolution images, we resize the high resolution images to a uniform patch size of 96 by 96 pixels. Low resolution images were downscaled by the required factors, and in some cases, they were upscaled also using bicubic interpolation. This upscaling was sometimes done to match the dimensions needed by some specific models like the SRCNN. Finally, the processed images are converted into PyTorch tensors, and this helps for GPU acceleration. Nextly, the models that we used are the SRCNN, which is the Super Resolution Convolutional Neural Network. It's one of the first deep learning models for super resolution. It has a simple yet really effective three-layer architecture. The first layer extracts features from the low resolution image using convolutional filters. The second one performs nonlinear mapping to refine these features. The third layer reconstructs the high resolution image at the end from the mapped features. This design allows the SRCNN to create a direct mapping between low resolution to high resolution images without any handcrafted features, making it really easy to train and computationally efficient as compared to previous methods. Then there is the VDSR, or very deep super resolution. VDSR architecture takes SRCNN on the previous architectures a step further by increasing the depth. The depth could be increased up to 20 layers, and it also introduces residual learning, where the network is trained to predict the difference or the residual between the low resolution input and high resolution output. This deeper architecture also allows VDSR to capture more complex patterns and details in images by focusing on residuals rather than the entire image. So, by using this, the network converges much faster and also performs better. Uh, the next, we have enhanced deep super resolution, EDSR. EDSR builds on the strengths of residual networks and takes optimization a step even further. It simplifies the architecture by removing unnecessary components like batch normalization layers, which can cause information loss and also introduce an additional computational overhead. The network, it consists of a head module, which is for pre-processing the input. Then there are multiple residual blocks, which are present for feature extraction and enhancement. And then there's a tail module, which performs the task of reconstructing the final high resolution image. EDSR also uses residual scaling, which stabilizes training by scaling down the residuals in each block. This model is designed for like great performance and gives a really good result. Now on to the training part. The pre-processed data set uh, is loaded into data loaders with shuffling and batching. Then the selected models, which are SRCNN, VDSR, or EDSR, are initialized and deployed on the GPU for acceleration. During training, we optimize the model parameters using MSE, or the mean squared error loss, and monitored progress through PSNR, which is peak signal to noise ratio. We did this on the validation set, and we also employed early stopping to prevent overfitting. So if the PSNR doesn't show an improvement for 10 consecutive epochs, we halt the training. We also implemented model checkpointing, where we save the versions with the highest validation PSNR. Then on to the results. All three models performed quite well, and EDSR achieved slightly higher PSNR and SSIM values. However, the differences are quite marginal, showing that each model is viable for practical applications. Here is the part about the full stack integration. We have a demo at the end, but essentially we have functionalities to upload an original image, a low resolution image. Then the model performs the models give an output for the high resolution image, and we also have some performance metrics which show the time taken to generate the result, and also tell about the image quality using metrics like PSNR and SR and SSIM. So these are some examples of outputs. Now onto the demo. Here we have a platform which allows us to upload images in any of the popular formats. So here we have the original image displayed, the low resolution image. And here we have all the three of the models trying to generate the output. And after the generation is complete, we also have the performance metrics, which include the time taken to generate these results, and also an assessment of the quality, which is in the form of PSNR and SSIM values. We also have functionality to download the resultant images by clicking on these buttons. And that's about it for the demo. Thank you.